Good morning, everyone. My name is Weina. Thank you, Jean, for the introduction. So today I will talk about the rheology control of ultra-high performance concrete, or UHPC in short. So first of all, I will talk about the rheology control for UHPC for better fiber distribution, three kinds of application. Better fiber distribution for slope casting, for ease of large-scale production. And given the importance of rheology control, I will also introduce a little bit about our ongoing work on the real-time monitoring of rheology, and then the conclusion. So why better fiber distribution? I think a lot of you already know that better distributed fibers will lead to greater flexural performance. A lot of studies, a lot of publications have given the figures like this. So also, based on our previous studies on the corrosion, we also found that the better orientation or dispersion of the fibers would improve the corrosion resistance of the rebar embedded into the UHPC. The reason is that if you have a better orientation of the fibers and better dispersion of fibers, there's less contact between the copper-coated fibers with the steel, and that could mitigate the galvanic corrosion and improve the corrosion resistance of a bar there. So, sorry, it's not working. So to achieve a better fiber distribution, Professor Zhang have introduced a lot of methods, and the key point is for the casting. In the casting point, we have to do proper casting. And for non-flowable or little flowable types of UHPC, usually you will need to direct the casting layer by layers from one direction to the other, and it goes back to orient the fibers. And for very flowable or highly flowable types of UHPC, what we usually do is to have a chute and let the fibers. That does not work. It's working. So you have a chute and let the UHPC flow from the chute and flow from one side to the other. So what happened in there is that during the flow, the fiber will be oriented in the shear zone. So there will be two kind of zone in a flow profile. Shear zone, there will be the gradients of the flow velocity, and that will apply a torque to the fibers and orient the fibers to the flow direction. And there is a plug zone. So plug zone here, the velocity of the flow is the same, so you will not have the fiber oriented. So for the highly flowable types of UHPC, we will want the thickness of a shear zone larger than the plug flow zone. So to do that, we will need to control the rheology. So basically, we want to minimize the yield stress of the mixtures or the suspending mortar to minimize the plug flow zone, and we want to optimize the viscosity to have a thicker shear zone. So the viscosity of the suspending mortar not just influence the fiber orientation, and a lot of studies also prove that it significantly influences the dispersion of the fibers in the matrix. So because of that, we will want to control the plastic viscosity or rheology of the suspending mortar for UHPC for not just the better orientation, but also the uniformly distribution. So one of the study, we investigated 6 different UHPC mixtures with different viscosity. So basically, we change the mortar with different viscosity by use different dosages of viscosity-modified admixtures, or VMA in short. So we have it from 0 to 2.5%. And here shows the mixtures, the UHPC mixtures we used. And the steel fiber here for this mixture is 2%. It's the steel fibers. So To have a relatively thinner plug flow zone, we should have achieve a relatively high mini slump flow for low yield stress. So here what we have is 280 millimeter plus or minus 5 millimeter. So we fixed the mini slump flow. And before we add in fibers, we tested the viscosity for the suspending mortar. So we use two methods. One is the mini V-funnel, and we test the flow time of the mixtures. And at the same time, exactly the same time, we investigated the actual plastic viscosity by using a contact viscometer. And from there, we established the relationship between the mini V-funnel flow time and the plastic viscosity, and we find there's a strong linear relationship between them. And after that, after we measuring that, we add fibers into the mortar and prepare the beam specimens, present specimens for flexural testing. And after we conduct the flexural testing, we cut the sections from the beams for quantification of the fiber distribution. So the concept here is we, first of all, establish a relationship between flow time and plastic viscosity, and we know that the plastic viscosity significantly influences the fiber orientation and the dispersion, and which will, in turn, influence the flexural properties of the beam. So eventually, we want to use a simple apparatus, the V-funnel, to control the rheology, and so that to control the flexural properties. So here shows the image, the binary images of two cross-sectional areas for the control mixtures and the mixtures with 1% of VMA, and we can see that using the VMA to increase the viscosity, improve the dispersion of the fibers. And also we use this image to quantify the fiber orientation coefficient, eta, and the fiber dispersion coefficient, alpha. So the eta and alpha, the higher values represent better fiber orientation and dispersion, respectively. So from our results, the flexural properties, as you can see, the increase of, so the flexural properties, specifically the flexural strength and the dissipated energy, which is calculated on the area under the flexure curves. It increased with VMA and then decreased. So as you can see here, so when the VMA equals to 1%, we achieve the largest flexural properties. And the increase, the reason for the improvement is mainly because with the increase of the VMA or increase of the suspending mortar viscosity, we increased the eta, the fiber orientation coefficients, and also the alpha, the dispersion coefficient. And we hypothesized that if we can use the VMA for some content to control the flow time of the suspending mortar to around 46 seconds here, then we can have the best fiber dispersion coefficients, and at the meantime, we can get the highest flexural properties. So to prove that, we change our UHPC mixture matrix from the fly ash-based one to slag-based one, and we investigated 3 different mixtures, and we use the VMA to control the viscosity or the flow time of the mortar for 60 seconds, 48 seconds, and 93 seconds. And as expected, when we control the flow time of the suspending mortar to around 48 seconds, we achieve the highest flexural performance. So the improvement of the fiber dispersion gives us the reason why we have an improvement in the flexural performance, but why there's a reduction there after the optimum viscosity. So this is actually due to the VMA. The VMA also have adverse effect to the matrix. It's introduced with more VMA, it will introduce more air to the system. More air means more of loss. And also more VMA, it will reduce the bond strength and the pull-out energy between the fibers and the matrix, so which would adversely affect the post-cracking behaviors of the flexural performance. So this is also validated by the SEM image analysis. So we can see that with more VMA, we will see like more pores in between fibers and the matrix. So this also gives us the ideas that VMA can improve the fiber dispersion, but also it will have adverse effect. So we have to find the balancing point, find the optimum to have the best performance for the flexure. So we also investigated the effect of fiber content on the optimum viscosity or the rheology control. So we found that the UHPC with higher fiber content requires higher viscosity or optimum viscosity of the suspending mortar to secure the highest flexural property. So here gives recommendations for the optimum viscosity for different fiber content. So you can always use the V-funnel, correlate to it, and use the V-funnel to control it. So that is the one application of rheology. So also for some of other application, we also need very careful rheology control for better quality. So this is second application for the slump casting. So for a slump structures such as the bridge deck, it's really have a slope structures with 2% to 5% of the slope. So I'm talking about highly flowable UHPC, it will flow from the top to the bottom, so which will cause some problem for the construction. So the desirable UHPC is that it's easy to mix, easy to place, but after placement, it can stay still. So to do that, we will need to develop or enhance the thixotropic properties of UHPC for the shape stability. So to do that, like a lot of researchers and producers use the nanoclay powders-based thixotropic enhancing the mixtures. But this type of nanomaterials, as the powders, it will prompt to agglomerate. So if it's agglomerates, it will not really give you a very good performance. And on the other hand, it will reduce the performance, especially the mechanical properties and durability. So you have to handle it with a good dispersion techniques, but that's hard in practice. So in our studies, we use the water-based nanoclay. It's used some surfactant to disperse it already in the liquids. It's a liquid-based one, so it's well dispersed. And we saw that it's very effectively enhancing the thixotropic properties of the UHPC and make it very shape stable after casting. So this is, we use that to control the so-called the rheology of it. And, enhancing the thixotropy will have adverse effect on the bond between the UHPC overlay and the substrate. So we saw that with the using of the nanoclay or water-based nanoclay, we increase the thixotropy, but at the same time we reduce the bond, mainly because by using that we introduce more air on the interface between the UHPC and the substrate. So it is suggested that we should apply a little bit of vibration for enhancing, the bond between substrate and the UHPC. So for each of the content of nanoclay, we have the optimum vibration energy that you can apply. So here shows what you can do. So the last application I want to talk about for the rheology control is for the large-scale production. So for UHPC, it's especially if you want to mix for a large volume, it's not easy, especially if you have if you just have the normal like pan mixer, not a very high energy kind of mixer. So this is mainly because for conventional concrete, it has high water-to-cement ratio. And if you investigate the mixing torque over the mixing time, kind of mixing kinetics, you will see that the peak mixing torque for conventional concrete is low, and is far lower than the capacity of the mixer. So it's easy to mix without any problem. But if you do UHPC, it's a different story, especially if you do a large volume. It has very high amount of binder and low water to semi ratio. And the mixing peak torque, especially with high volume, it's very, very high. It's easy to surpass the capacity of the mixer if you mix at one time. So that will cause the stoppage of the mixer. So the simple way to control this type of rheology is instead of pour all the raw materials one time, we equally divide it into 2 or 3 parts, and we add 1 part after another. And what that means, here you can see that if you do 1, the peak mixing torque will surpass the mixing capacity of the mixer. But if you do 2 or 3 batch, and you can significantly reduce the peak. And as you can see, So as you can see here, So if you do mono batching, stop. If you do 2 or 3 batching, very smooth mixing. So given the importance of the rheology control, we also developed the AI-based methods to assess the viscosity in real time. So this is actually because we know that the difference in viscosity of the fluid, as you can see here, can be visually identified by its morphology and things like that. So we developed the deep learning methods we take videos during the concrete mixing, and we use deep learning to identify the features of the videos and also the sequence of the images in the videos and output the plus viscosity. So here shows that the videos are composed of many, many images, so we can identify features of the images and also the sequence. And based on that, you can use any kind of camera, even the phone, to take the videos during the mixing, and it will output automatically the plus viscosity. And compared to other types of methods where we are like real-time kind of monitoring without interrupting the mixing. So in conclusion, sorry, I'm a little long. So in conclusion, we have using the rheology control to control the fiber distribution and to enhance the thixotropy. But with the enhanced thixotropic properties, you will need to apply a little bit of vibration for improving the bond. And also, we need to optimize the casting methods or procedures for large-scale production of UHPC. And also, we can try to use the AI-based method to monitor the viscosity in real time. And for all details of the things I just presented, you can find in our papers listed there. And I would like to thank all the contributors to all of the work, and a special thank to my PhD advisor, Professor Kamal Kayat. And that is all. Thank you very much for your attention.